So you're going to be working with numbers. There's the big scope of numbers. There's all the numbers that there are. There's something called imaginary numbers that we won't work with for a while, so we'll just forget about those for now. Okay. We're going to be working with real numbers. Okay. Now that's not a big jump because that's all you've ever used, really. You may have used imaginary numbers. I don't think that you probably have. Okay. So let's start down here at the natural or the whole numbers. These sets of numbers have names. We're going to name them. Okay. So the whole numbers are 0. It's basically like how many of a thing you can have. You can have 0. You can have 1. You can have 2. You can have 3, and so on. Those are the natural numbers, the whole numbers. Okay. If we go to the integers, they're a little bit, I won't say bigger, but there's the integers. We expand a little bit off the natural numbers. So we have 0 and 1 and 2 and so on. We also have -1, -2, and that direction too. So we have all the positive whole numbers, not decimals, not fractions, not parts of numbers, but entire numbers. And then we have the integers includes the negatives. Okay. How about a rational number? What's a rational number? Anybody? How about based off the word ratio? What's a ratio? What's a ratio look like? Fraction. Yeah. So they're the fraction numbers. So we got rational numbers like 3/4 and 7/16, and even improper fractions, 1/35/7, all that kind of stuff. Those are all rational numbers. Okay. We even have decimals can be rational numbers. This is 0.75, and this is a decimal I don't know. And let's see, I'll pull one over here. 1/3 is 0.3, and we repeat that 3 forever and ever and ever. That's 1/3. That's a decimal equivalent to 1/3. Okay, so those are all rational numbers too. And so a rational number is any integer over another. So we talked about integers. We have these guys are integers. Okay, if you put a rational number, if you put like 7 over 1, you're in the integers. And even more specifically, since 7 was positive, you're in the whole numbers. Okay, so the rational numbers include the integers and the natural numbers. Does that make sense? This is nested in that, and that's nested in that, so we have those kinds of numbers. So the rational number is any integer over another integer. So it can be positive, it can be negative, it's any entire, not part of a number, one over the other, or a decimal that is equivalent to a fraction. Including 0.3, repeating, or really any repeating decimal. Any decimal that repeats can be written as a fraction. Okay, a rational number. Okay, anybody know any irrational numbers? Irrational. Numbers that cannot be written as fractions. Yeah?
Pi.
Pi is an irrational number. It's one that we're all fairly familiar with. Okay? 3.14159, and just keep going, there's some more. Right? And it's calculated to a trillion digits, maybe more now. So it just keeps on going. E, that's a number we'll learn about. It's a number. 2.718, there's a number phi. Okay, it's the golden ratio. So there's lots and lots of different irrational numbers. A lot of them have names that we give them with Greek letters. And those are examples of decimals that go on forever, they just don't repeat. Okay. So any decimal that ends or repeats can be irrational, and other ones are irrational. Okay? So that's a quick shot of what numbers are, what they're called. If I reference an integer, then you know we're talking about these guys. They're not fractions. They're whole. These are whole numbers. There's whole numbers. There's a different set of numbers. But they're numbers that aren't parts of numbers, and they could be negative. Okay. So let's talk about the properties of real numbers. So first, these are the kinds of things that you do in math, and I think they're kind of fascinating and fun. So we have to state some conditions. So we say if A and B are real numbers, then there are certain things that we need to know about them, things that they can do with each other. For one thing, if I add two numbers together, two real numbers together, what do I get? Yes?
A real number.
Another real number. You won't add two real numbers together and get an imaginary number. Okay? And the reals are all of these, rational and irrational. If you add those two together, the result will be real. That's what you call closure. The set is closed. You can't escape the set of real numbers by adding two real numbers together. It's closed. Okay. Now there's commutativity and associativity. How many of you have heard of those two? At least heard the words? Right? I had one on the test, one property on the test, just to see how you guys would do. You know, about like I thought. Those things slip your mind. You don't remember those things. So let me help you with a little bit of looking at the words. Okay? It's some reasoning that we use about what the words are and how they apply to the property we're talking about. So commutativity is to say that A plus B, let's just say is real. So A plus B is the same as B plus A. It's commutativity. What's the root word of commute? Of commutativity. What's the root word? Commute. Very good. What does it mean to commute? Who commutes? What do they do when they commute? Any example of commute definition, or use it in a sentence?
To go from one place to another.
One place to another. When I come to work, I commute from home to work, and then I commute back. Okay, that's commuting. There's movement. Okay, do you see why that might apply to this rule? They moved, but they gave the same answer, right? So there's movement. They actually move. They commute. A commutes over here. It moves, but you get the same result when you add them together. Okay. Associativity says that A plus B first plus C is the same as A plus B plus C first. Okay. What's the root word of associativity? Associate. What does it mean to associate? Or what do you think of when you think of associating? Gordon?
To communicate.
Okay, communicate, talk to somebody, right? And what do you do when you associate with someone? If you go up to somebody at a party and talk to them? You probably like look at them. You guys have some kind of interface going on, right? Right. So if you guys were to look at each other, you could associate with each other. You guys could associate with each other, but there's no one has to go anywhere. Nobody has to commute anywhere. We're just talking about the association that A and B are going to have with each other. Okay, they're going to add each other together, and then C will come in. It's the same thing as if B and C were to associate and just turn and talk to each other and add to each other, and then add A later. It's the same thing. Okay, so that's just a memory thing. I don't really love memorizing stuff, but sometimes I'll say, oh, addition is commutative, right? I'll use that word. And I want you guys to be at least familiar with what I'm talking about. We switch the order of what is in front and what's second, and it doesn't make a difference. And not only is addition, is there closure under addition, not only is addition commutative, and not only is addition associative, what else is closed and is commutative and is associative? Subtraction, it's really, you're talking about addition, but if I did A minus B, is that the same as B minus A? No. Negative numbers, though. You know, as long as the negative goes along with that number, that's the same thing. Chloe? Multiplication is all these things as well. So A times B is real. That's also a real number. Real. A times B is the same as B times A. A times B first, then times C is the same as A, hold on a second, A, B times C first, and times A later. Okay? So they both have operator, and multiplication is an operator. And now, technically speaking, the real numbers only are added together and are multiplied together. Okay. What are we doing when we subtract, really? We're adding the opposite. Adding the opposite, adding a negative number. Right? If you're subtracting 5, you're adding the opposite of 5, adding negative 5. Okay. And when you divide, you're really multiplying by, well, it's inside the rational numbers here. Right? It's a fraction, the reciprocal, the reciprocal of that number. Okay. But those are the properties. So if you need to identify properties, there they are. Commutative, commute, move. Associative, don't have to move. You just associate with whatever's around you. Okay. Okay. So you have the distributive law. So if A, B, and C are real numbers, then can somebody use A, B, and C and show me the distributive property? At least you can do it? Come on up. So you're gonna just write something that displays the distributive property, how it works and where all the numbers go and all that. Okay, and then what does distribution look like? How do you distribute that A? And then the new thing, let's say equals what? Equals yeah, A times B. There you go. Perfect. Thank you very much. Okay. So I'm just gonna, just to remain consistent, I'm gonna rewrite what you have here with the lowercase letters. 'Cause, we'll learn over time that sometimes it matters whether we're using uppercase or lowercase letters when it comes to variables. Uppercase letters represent different kinds of things than lowercase letters. And not because it's the right thing to do, it's just the way we agreed to do it. Okay. Okay, so that's the distributive law. And I think up to this point, most of you did pretty well on those topics. So we won't spend a ton of time. But one thing was, just a couple, when you went to compare, well, when you went to graph numbers on a number line, if we were going to graph negative 4.5, just make sure, like if there are marks here, and you put a mark right there and just call it negative 4.5, does that work?
No,
What do you need?
a 0.
You gotta have some reference to scale. So let's see, 1, 2, 3 and a half. No, 0, 1, 2, 3, 4 and a half. So there's 0 and negative 4.5. So when we graph things, when we start to do more graphs, we gotta pay attention to scale. Scale has to make sense. Right. Okay. Fractions, we'll spend a little bit of time on because I don't know if there's been a generation yet that's just been like, yeah, fractions, they're great and I love them. Alright, so let's talk about adding fractions. Alright, so take, let's see if I can find, I know one that I'll bring up in a minute. First, we'll add two fractions together and we'll discuss what that takes. And we'll make this 6, and we'll make this 4. So 3/6 plus 3/4. We'll add those together. we're gonna add 3/6 and 3/4. Is there something that we need?
Common
We need a common denominator, okay? Now, if you could express this, could you tell me if anybody doesn't understand why you need a common denominator? Is anybody who doesn't understand why you need a common denominator? You just do it. You know that's supposed to be done. You know those numbers need to be the same, but you don't really know why. Tristan, okay? So when you see two fractions and you don't know why you need a common denominator, I mean, what are you thinking? How would you combine those if you were to just like follow your instincts?
Not sure.
Okay. I'll just do 5, 6. Let me see if I change this. Okay. So you just see those and you have a notion of what they are, right? What a fraction is, okay? What is 5/6?
It is 5 pieces out of a 6.
Out of 6, and 6 of those pieces would be
A whole.
a whole. Yeah, there's 5 out of the 6, 6 being the whole thing. Okay. Anybody have a suggestion? Maybe something you did at a younger age, how you would add these together without finding a common denominator?
When I was younger, I just add the top and the bottom.
Add the top and add the bottom. Okay. So the thing about that is, why did you do that?
Well, before when you did addition, you just added the numbers that were there, so.
Yeah. You just try to follow the old reasoning, the old rule of adding numbers. You add the top ones, add the bottom ones. But we know that's not how it works now, right? We really want to get why it doesn't work. Now I can't say what adding the top numbers and the bottom numbers would even mean. Like I can't even construct a concept of what that would represent because it's just wrong, right? So what it is, we have like that. We've got 6. There's 5 of those 6. Then we have 4ths. Here's 3 of those 4ths. Okay. So if I were to put all of those together, and I were to say, let's say we just add these numbers together, we get 8. 8 what? What would they be? Anybody answer that question? Tenths. Okay, let's look at what a tenth would be. A tenth would look like this. Cut into 2. Doing the best here, not bad. Right? A tenth would be, a tenth would be 1 of 10 pieces, where 10 of those pieces makes the whole. Right? Well, I mean, maybe it just doesn't seem that way. Like we can't even say that they're 8. Right? 5 plus 3, 8 anythings. Let's see. If there were 8 tenths, then we would take these two things together. So we've got this little piece missing and this little piece missing, right? If we were to add them up, we'd have 8 tenths, maybe. Does this seem right? That much and that much put together is this much? No. So, no, that didn't. And the thing about saying that there's 8 of something is that there's 5 that definitely look one way and are a certain size, and there's 3 of these that are completely different. So you can't even say you have 8 anythings. It's comparing apples and oranges. If I had 5 apples and 3 oranges, and I tried to add them up and say I had 5, there is no unifying what they are. And they fit the category of fruit. You can say you have 5 fruits. But that wouldn't have gotten us anywhere. We could add them and say we'd have 8 pieces, but we don't know how big those pieces are. Okay, is that making some sense? So what do we need to do? Like we're trying to add things together. We're trying to compare things that aren't the same. They're apples and oranges. So how do we make them the same? Don't worry about those numbers there. What would you do with these? How would you make them the same? Well, these pieces are this big. These pieces are this big. we hopefully grab a different color. Well, maybe we could cut these pieces into smaller pieces so that all the pieces are the same size, right? So one surefire way to do that is to cut each of these pieces into 3, right? And each of these pieces into 4, and each of these pieces into 6, right? So then all of the little slivers would be all the same. Okay? So we cut up the pieces, cut up the entire pie up into pieces equal to the number of pieces that we have over here. So we get 4 times as many pieces over here, and 6 times as many pieces over here. So we have 6 pieces times 4, 4 pieces times 6, and now the two pies have the same size pie pieces, and we can compare them, right? All right. So that's what we have here. We have 5, 6. So we would take the total number of pieces, multiply that by 4. Okay. But obviously, that whole contains these 5. Those 5 would also get multiplied by 4. Does that make sense? All of the pieces would get multiplied by 4, and also these 5 would get multiplied by 4. And over here, we would cut each of these into 6, so we'd cut each of these 4 into 6. And obviously these 3 we can cut into 6. And now each pie will have 24 pieces, and now we can compare apples to apples. So we have 20 24ths plus 18 24ths. Now there's something that's the same. Now we've made them comparable. So now we get 38 24ths. And that unifies them together. Okay? Now, we've heard of common denominators many times and done it for many years. And so this is to serve as maybe an aha moment where you see, oh, that's why we're doing what we do to the numerator and denominator. And that's why we're trying to get the denominators to be the same thing. Right? And I don't think it's a waste to spend time on that because I've taught math for many years, and this is an issue every year for every class, whether it be Algebra 2, Pre-Calculus, or Calculus. Everybody just continues to have problems with it. So to get common denominators, what would you say the process is in general? How do we find that number that they can?
Finding that, is it a factor or a multiple between it and that?
So which is which? What's a factor and what's a multiple?
A multiple is something you multiply.
So with 3 and 12, these two numbers, which is a factor and which is a multiple?
3 is a factor.
3 is a factor of 12, 12 is a multiple of 3. Yeah, okay. So if we go back to 5 6 plus 3 fourths, I'll just write that back over here. That's not right. 5 6 plus 3 fourths. So what are we trying to do then?
Okay. You find their their least common multiple and then multiply whatever you multiply the bottom number by on the top.
Right. And let's least common multiple. So what's a multiple?
The product of multiple numbers.
Yep. You take a number, you multiply it by another, the result would be a multiple. Okay. So if we're talking about common multiples, if we bring this word into it, then we have 2 or more numbers and they have some multiple they can both go to. Right? We multiply them each by some number and we get some multiple that's the same thing. And there's not just one common multiple, there's lots and lots of common multiples, so that's why we specify and say we want the least one, the smallest one, smallest common multiple. Now is 24 the least common multiple between 4 and 6? What is it? 12. So we could have even made this easier by going to 12. So we can multiply this by 2. Multiply this by 2. Right? Means it would be the equivalent in this analogy of cutting each of these pieces into 2 pieces. And multiply this by 3. And so we would get 10 twelfths plus 9 twelfths, and we get 19 twelfths. Okay, and what's the advantage of 19 twelfths over 38 24ths?
Have to reduce as much.
It's already, and I like the word simplified, because it's better. But when you use the word reduce, people, a lot of people have this misconception that when you reduce it, it's a smaller number. Like somehow this fraction is bigger than this fraction. Right? Is this fraction bigger? No, it's the same as this. We've divided the numerator and denominator by the same number. Divide them both by 2 and we get 19 twelfths. Okay? Alright. And before we put these fairly basic examples of common denominators to bed, are there any questions about it? Then, there's more about fractions we need to know. And so the same goes for subtracting fractions from common denominators. It's all the same. So we can take fractions and we can multiply them together. So how do we multiply these together? Gordon?
You just multiply straight across.
Multiply straight across. 6 35ths. Okay? Now that's comes fairly easy, I think, for most people. They just multiply straight across. I don't see many people getting confused about that. What do we get confused about though? When you divide fractions. What do you do when you divide? Can't divide fractions? Gotta be able to divide by fractions. I mean, they're numbers.
You multiply by the reciprocal.
You multiply by the reciprocal. The reciprocal of which one?
Doesn't matter.
It doesn't matter. Oh. Okay, so let's investigate all this. Let's investigate. So we'll just take these two again. It's gonna be totally different. We'll just divide them like this. 2/5 divided by 3/7. Right? So I hear multiply by the reciprocal. So what does that mean? What would my new problem look like?
2/5
Times 7/3. Okay. That's correct. That will get you to the right answer. Okay. So 14 over 15. So that does it. That gets us there. But let's understand a little better why. Why that's the right answer. I think this helps you to see it visually. If you have a problem that's 2/5 divided by 3/7, I would suggest you write it like this. Okay. Now, in the numerator and denominator, I can multiply by the same thing, right? We did that when we added fractions together. We multiplied the numerator and denominator the same thing. I got common denominators. Another thing, just to display that that's true, let's say I multiply the numerator by something, and I multiply the denominator by the same thing. Well, what is a divided by a?
1.
It's 1. So all I'm doing right now is I'm going to multiply by 1. And that's not going to change anything. When you multiply by 1, that's called the multiplicative identity, and nothing changes. So what I'm going to multiply by is 7/3. Okay? Why is that useful to multiply by 7/3 in the denominator? Cancels it out. You get 7's cancel, 3's cancel. Or if you don't like the canceling, let's just see what happens when we just do the math. 3 times 7, 21. 7 times 3, 21. 21 divided by 21, 1. What about when you have 1 in the denominator? It's just that number that's at the top when you divide by 1. So divided by 1 is like nothing happens. So now this is kind of, canceled out, negated. It's gone in a way. So, but we also need to multiply the numerator by 7/3. So we get that. This is all 1. Okay. This is all 1 in the denominator. And now we just multiply together. 2 times 7 is 14, and 5 times 3 is 15. And divide by 1, it doesn't change anything, so we have 14. This. So a common mistake I see, especially if it's written like this division symbol, is people will take the reciprocal of the first fraction because they memorized multiply by the reciprocal and they don't know why they're doing the reciprocal of the one that they're doing the reciprocal of. They just memorized what they're supposed to do without knowing why it works, or even be able to justify that it could work. Okay. Are there any questions about fractions, adding, subtracting, multiplying, or dividing fractions? Okay. So, number 40. What is number 40? Okay. Rates are really, really important in this class and in classes beyond this class, so you should understand them. So, let's say rates of change. Can somebody define a rate of change? What does it mean? Something is a rate of change. Or give me an example of a rate of change. No example of rates of change? Okay.
Like 0.5 per year, something like that.
Something like that? Do you have that?
Pretty much.
Pretty much you had?
Yeah.
Yeah, and that was,
0.5 per year.
that's what it was. And to be honest, I looked at this question again, and the wording was not so great. They weren't clear what they wanted you to do. So what they wanted was the annual rate of change. How much is the pollution level changing every year? Right? So they want parts per million, the amount of pollution change, in a number of, 1 year. They want it to be down to 1 year. Okay, so the amount that the pollution changes every year. So how do we do that? What do we know and how do we find it? How do we find the rate of change? Reese?
You take the larger number and subtract the smaller number, and then how many years there were
Yep.
in between them, and then divide the outcome of the two numbers by the amount of years.
So you took 4.4 minus 1.4,
Yep.
and that's, what does that represent?
Per million a year, or whatever.
Well,
First one.
just this subtraction represents the change in pollution from the end, or from the beginning to the end, right? So at this point, without writing anything else down, we don't really know what's the beginning and what's the end, like when it was. But we know that this was the beginning, and this was the end. We take the end result, subtract the beginning result, and we find out how much the change was. We know the difference between that. And in the denominator, we take the number of years. How many years went by? 6. So subtraction, maybe not completely necessary. 1983 minus 1989 minus 1983. We know that's 6 years. Okay, so 4.4 minus 1.4 is 3 parts per million for every 6 years that go by. And if we divide 3 by 6, we get 1/2. part per million per year. A half of a part per million of pollution was added to the atmosphere every year. So rate of change is just, it's a ratio. The change of one thing to the change of some other thing. Yeah?
Wouldn't you read out 1 per every 2 years?
You could. It's you could read it either way you want to. But if you want the annual, and I know that wasn't in the question, and that's the problem. That's the flaw in the wording of the problem. So you could say 1 part per million for every 2 years, 1/2 of a part per million every 1 year, 3 parts per million for every 6 years. They're all the same thing, right?
Mm-hmm.
If we were to take any of those, which they're all equivalent, and then just observe it for 1 year, how much would we see it change? Half. If we watch for 2 years, we would see 1. If we watch for 6 years, we would see 3. If we watch for 12 years, we would see 6. And it all is the same. It's a rate of change, and that stays consistent for however many years you want to look at it. Okay. So a rate of change is just, depending on what you want to know, it's just how much one thing changed versus how much another thing changed. Okay, over a span of time or over a distance or whatever. Okay. Let's see. We'll talk about exponents and where we can run into trouble with exponents. Let's look. If I take some number and I square that number, what am I doing with that number? Yeah. So x times x, multiplying x by another x. Okay, so if I do x to the third, what am I doing with that? Multiply x 3 times. Okay, and the thing is, whatever that number is, that's the thing you multiply by itself that many times. Okay. So one thing that I saw that happened quite a bit was this. If I say take x squared and then evaluate it, something like this, evaluate for x equals -6. Well, what does that mean? Make x equal 6. You just take x, replace it with -6. Right? So this is what a lot of people will do, whether they write it down or they do it in their heads. Okay? Now here's the thing. But this gets to something called the order of operations, which we'll have another video on that one too. It comes down to the order of operations and what we agree, like how we write things. How we agree what that means. Does that make sense? When we write a period, it's not intrinsic, it's not like we can do some calculation and figure out a period is the symbol we're supposed to use to end a sentence. It's just the one that we do use. Right? So it's an agreement that we make. So the agreement that we have in math is that if I write an exponent above a number, right, just immediately above whatever I am applying it to, that's the thing that I multiply by itself. Okay? So this applies only to the 6. But am I supposed to square 6?
Sorry.
I'm supposed to square -6. So I'm supposed to square x, and what is x? -6. I'm supposed to square -6, the whole thing. How do I indicate that I want to square the whole thing? Parentheses around the -6. Okay? So, and like we said, anything that you square, you multiply by itself. Okay? So negative 6 multiplied by negative 6, and what will that be? Positive 36. So that's a big thing, because a lot of people will mistakenly get, what do you think? Negative 36. So just square 6, that's 36, put the negative on it, and get negative 36. So that is just a common pitfall that people fall victim to. Okay. I think that's, no, that's almost as far as I wanted to go. So you want to talk about what the book calls simplifying algebraic expressions, or what you might call combining like terms. Can someone define in their own words what it means that something is like terms? That two things or three things are like terms. Gordon.
If you have like x to the fifth and x to the third, you can combine them and make x to the eighth.
How can you combine them?
You just add the exponents together.
What you say, if you have x to the third and you have x to the eighth, like in what way are they being, what operation are you using? Are you adding these things together?
Yeah.
You're adding these
You
things
can add
together?
exponents. And then
So if we add this together, we can get, what would we get?
x to the 11th.
X to the 11th. Okay, let's see, what if we had 5x to the third plus 2x to the eighth? What would that be?
Can you combine that?
We should be able, if we can combine that, we should be able to combine that. 7x to the 11th. Okay. Can we justify that with what we know about addition and exponents, multiplication? What does x to the 11th mean? What are we doing with x?
Multiplying it 11.
Multiplying by itself 11 times. Let's see how we wound up with that. What are we doing with x here? Multiply by itself 3 times. And then what are we doing separately with this x? By 8 times. So if we multiply this by itself 3 times, multiply this by itself 8 times, and we want it to equal x to the 11th, which means we multiply it by itself 11 times, what would we have to do with these two groups? Well, if we want it to equal x to the 11th, which is x times x times x times x times x times x, like all 11 x's are multiplied together, what would we have to do with these 3 and these 8 x's? We have to multiply. You have to have a string of multiplied x's. But we didn't multiply them, we add them together. Right? Completely different operations. Addition, multiplication. We can't add them together and multiply them together. Right? That makes sense? So this is a group of 3 x's, this is a group of 8 x's being multiplied together. They're not the same thing. We can't compare them, we can't put them together. What we can put together is 2 x's, 5 x's. How many x's are there?
7.
There's 7 x's, right? Because what's 2x is just x plus x. And what's 5x is just x plus x plus x plus x plus x plus x. And we're adding those two groups together. What do we have? 7 of those things being added together. And a short way to write that would be, with multiplication, 7x. Okay. So, you might say those are both x's, right? So they're like terms so I can combine them. But they're not the same thing. Yeah?
Can you combine, like, if you had like 2x to the third and 3x to the third?
Yeah. Just 2x to the third plus 3x to the third.
Since they're both to the third, you can combine those.
Right. Because what we really have is x to the third plus x to the third. That's 2 of them added together. That's why we write 2 times x to the third. We're adding those 2 together and we're multiplying to write it shorter. And then we have another x to the third and another x to the third and a third x to the third. Third one. there's 3 of them added together, and so together we have 5 of all the same thing. Okay. So the common mistake is this. Which is, can't do any of that because they're not like terms. It's like trying to add the 2 things with different denominators. They're just not the same thing. You're not comparing apples to apples. You're comparing apples to oranges, and they can't go together. Okay. Now this I'm going to talk about this, how we could actually get x to the 11. This isn't really combining like terms. It's something a little bit down the road. If we had x to the 3rd times x to the 8th, okay, and don't get caught up in remembering this rule when you multiply, you add the exponents. Just think. Well, we have the situation we were needing to have before. We have 3 x's multiplied together. We have 8 x's multiplied together. And I choose 8 as a big number. And we're multiplying all those together. Now that's exactly what the definition of x to the 11th is. 11 x's being multiplied together. X to the 11th. Which would just be the equivalent of taking 3 and adding 8 to it and saying x to the 11th. Okay? The main thing though is not so much this, it's more adding and subtracting of common like terms. Okay? X squareds and x squareds, you can add those together. X to the 3rds and x to the 3rds, you can add those together. But when you have things that are different, especially this is probably the most common one that I see, 5 plus 2x is 7x. You add them together, it's 7x. I know it's tempting, but we just need to remind ourselves, look, this is a number x, and it's being multiplied by 2. And then we're just going to add the number 5. That's not the same as taking the number x and adding it up 7 times, right? It doesn't compute, especially if you add it like this, 5 plus x plus x. And there's just the number 5, and then there's 2 more numbers that both happen to be x, and so we shorten it by writing 2x, and then you're done. There's no more combining to do. Okay. So in that vein, if we were to together in a number like 18. 4 times 1 minus 5 times x minus 1. Alright, so if we want to put this together, first we need to do, and don't think order of operations. I'm going to like try and unteach you order of operations because it's, we'll talk about it then. But don't think, what according to the order of operations, exponents, parentheses, multiplication, division, like what am I supposed to do first? Just, look at it and think, what would make sense to do first? Do the stuff in the parentheses, which it was a great idea. We just, we can't put them together, right? There's no like terms, and so now we're stuck with needing to multiply by 4 without being able to combine those, right? So how do we multiply by 4? It's the distributive property. 4 times x, 4 times negative 1. That's the result of that distribution. What are we distributing to this parentheses? Negative 5. Okay, so negative 5 times x, negative 5x. Negative 5 times negative 1 is 5. Okay. The thing that you need to be careful of here, I saw quite a few people get like 9x plus 9, or something like that. How'd that happen?
Combine like 2. Combine like the 5 and the 4.
Oh, this 5 and that 4?
It's negative ones.
I think more likely what happened was they saw a 4 and a 5 and made 9. And didn't pause and say, no, that's 4x minus 5x. It should be negative x. It's just I think a matter of rushing too quickly. Negative x, negative 4 plus 5, that's just a 1. let's just make this up as an example. Say 9x plus 4 minus 6x minus 1. We go to simplify this. Well, 9x minus 6x, get 3x. Plus 4 minus 1, well, that's just 3. And then people divide by 3. You get x plus 1. Okay. Anybody attempt to divide by 3 when you get here? Nobody? Well, some people are. I've seen it. The reason you do that is because you're thinking of solving an equation. You guys have solved equations before, and you know that at some point when you have a 3 and an x, you divide the 3 away from the x, right? But are we solving anything? There's nothing to solve. It's just an expression. It's just 3x plus 3. 3 times the number x plus some more, plus 3 more. And if you divide it by 3, it's like just taking, if I say, hey, here you go, here's the number 9. That's for you. You can have the number 9. It just needs to be the number 9. You just say, okay, well, I'm going to divide it by 3, and you gave me the number 3. It's divided by 3. It's divided by 3. Right? You took a number that exists, it's a certain size, and you just divided it by 3 out of nowhere. Okay, that's what this is. So keep in mind that dividing by 3 is there in your rote memorization because you're thinking about equations, which this is. And what does this need to be? What does this need in order to be an equation? An equal sign. Gotta have an equal sign. That's what makes an equation an equation. An equal sign. Okay. So that's combining my terms. And this will lead into order of operations. Let's see. But I ran out of the chocolates. Just called evaluating an algebraic expression. So if you have an expression like 2x plus 7 minus x, evaluating it would mean that you have to be given a value. So evaluate it for x equals 3. What does that mean to evaluate that expression for x equals 3?
You insert the 3
Put 3 into the x. So 2 times 3 plus 7 minus 3. You can do that. Yeah, 6 plus 7 minus 3. And that would be so evaluating just means plug it in there. So let's, in your homework, you're going to need to do that. You're going to need to evaluate an expression. You're going to be able to plug something in. And that's going to include the topic of order of operations. Okay? So can somebody tell me what the order of operations is? Okay. So, and how do we remember that? Right, PEMDAS. Okay. So let's see. I'm just going to show you the video that I want to show you, and let's see what you think.
This test paper behaves like the surface of your skin. Now watch what soap does to it. Soap strips your
That's
skin.
bad.
Dove is different.
Dove is
With
good.
1 quarter moisturizing cream, Dove doesn't strip your skin like soap.
Wait, did they just say Dove isn't soap?
By Dove, that's what they want you to
Dove
do.
doesn't strip
By
your
Dove.
skin like soap.
Isn't that going to
better than.
That makes sense, actually.
Why do you question everything? Why can't you just, it's
Fun.
This test beaker behaves like the surface of your skin. Now watch what soap does to it. Soap strips your skin. Dove is different. With 1/4 moisturizing cream, Dove doesn't strip your skin like soap.
If you went to elementary school in the US, or much of the rest of the world, you almost certainly learned about something boringly called the order of operations, a set of rules for whether or not you should do multiplication before addition or addition before subtraction to get the right answer on your math test. Except you don't always get the right answer, or even one answer. I mean, is 8 minus 2 plus 1 equal to 5 or 7? And is 6 divided by 3 divided by 3 equal to 2/3 or 6? The problem is, focusing on the order of operations can lead to ambiguity and obscures the real, underlying, and often beautiful mathematics. A mathematician will tell you that 8 minus 2 plus 1 is really 8 plus negative 2 plus 1, which is unambiguously equal to 7, even though the so-called order of operations standard in the US tells you the answer is 5. If you want 5 for your answer, then you really need some parentheses. But why is this ambiguity even possible? It's because fundamentally, all of these operations are simply different procedures that start with two numbers and combine them in some way to give you one number. Each operation takes two numbers as input, 2 and no more. If you want to be entirely unambiguous and pedantic, every single pair of numbers in any algebraic expression should be inside parentheses. And then there's no need to know any order of operations. Just evaluate the innermost parentheses first and work outwards, collapsing them down pairwise like a championships bracket. But it turns out that's not the only way. It's possible to change the order in which you do the operations, to rearrange the parentheses, as long as you know what the underlying mathematics is. For example, if you want to add 3 plus 4 and then multiply the result by 5, you can either do the addition first and get 7 times 5 equals 35, or you can do the multiplication first, as long as you know that multiplication distributes across all the terms in the parentheses. That is, 5 times 3 plus 5 times 4 equals 15 plus 20 equals 35. The same answer. And how do we know multiplication distributes? One way is to draw rectangles, but I've done that before. The same rearranging can be done for exponentiation and multiplication. 3 times 2 all squared, or 6 squared equals 36, is the same as 3 squared times 2 squared, 36. It even works for addition and subtraction. 5 minus 1 plus 2 is 5 minus 1 minus 2. So the true order of operations is this. Use parentheses and learn what exponentiation, multiplication, addition, and the rest are really doing. Then you can proceed however you want. That's not to say that we don't have a conventional order of operations in mathematics. I mean, deciding that we evaluate multiplication before addition allows us to get rid of lots and lots of redundant parentheses. And noticing that 1 plus 2 plus 3 equals 1 plus 2 plus 3, and 2 times 3 times 4 equals 2 times 3 times 4 removes a ton more. But the point is that those parentheses are still there, still implied, just like how 3 minus 4 is secretly implying 3 plus negative 4, and 3 divided by 4 is really 3 times 1/4. But anytime the result might be ambiguous, you really need to use parentheses. Then you can proceed in whatever order you want. The order of operations learned in school, however, is different. It's a mechanical set of instructions that dictates just one of the many ways you can do algebra. It locks you into a single path through the beautiful mathematical landscape, which, while necessary for a computer whose goal is merely to give you the right answer, doesn't really give any insight onto what it is that you're doing when you do algebra. So while the order of operations isn't technically wrong, because most of the time it'll give you the standard answer, it's morally wrong, because it turns humans into robots. This Minute Physics video was brought to you by Squarespace, the only...
Okay. So, order of operations is morally wrong. What you're saying?
one platform that makes it fast and easy to create a professional website, blog, portfolio, or online store.
Okay, so you see what he was saying? Gordon?
8 minus 2 plus 1 will always be 7 because you're supposed to proceed from left to right.
That's an order of operations.
Yeah.
It's like the agreement that was made.
Yeah. I'm just saying that if you did it right, it would never come out as 5. You said it
Yeah,
would.
but it's right. what's right?
To proceed from left to right.
Why is it, he says that there are operations, addition, let's say there's like 5. There's really addition, there's multiplication, and then you do them multiple times or whatever. But there's just the two numbers interact, and they create a new number, right? To proceed from left to right is just something that's convenient for us because we read from left to right, so it just makes more sense to us. But there's nothing about combining numbers that tells us that if you have a string of numbers, you would have to go from left to right. Right?
Yeah, you could arrange the order of operations however you felt like. If you wanted.
Exactly. That's what I'm saying. So to teach students that there's only one order of operations and you must follow it, and it is PEMDAS, it's misleading, and it turns you into a robot. Like, you're a robot. You're stuck in this. You gotta proceed this way. Now it's convenient for us all to get together and to agree that we'll proceed this way, and that multiplication will come first, and then addition and subtraction will come next. Okay? But there's nothing that tells us that's the way that it has to be. If I write 5 times 3 minus 6, you've been taught enough to know do 5 times 3 first. But there's nothing that tells you that you can't do 3 minus 6 first, and then multiply. Right? There's two numbers, they could interact, 3 minus 6, and then you could get a new number, -3, and they could interact with 5. Okay? So the order of operations is not about you being right about math. It's just about, like if I teach you order of operations, I'm just cluing you into what the agreement is. Right? We talked about that earlier. We made an agreement to end sentences with periods. We could have used any symbol, that's just what we use. In fact, there's a student from Spain who saw a number, something like this, and she calls me over and she says, is this a comma? Is that what that's supposed to be? Because in Spain, in a lot of European countries, this is what they use for a decimal, right? That can be very confusing. Their agreement in Europe is different from our agreement over here, right? So it's all just about what we decide. We decided it to do this way. So I don't want you to think that there's a right way to combine numbers and a wrong way, but a way that we've agreed to and a way that we haven't. Yeah.
If we use decimals, like a point to
Yeah.
separate decimals, and a comma to separate like
Sets of
hundreds,
3 zeros,
thousands,
yeah.
millions, what do they use to separate the hundreds, thousands, millions?
I don't remember. I just read some papers that were written in like Spain and places like that, and they use commas. I'd have to look that up. If you keep reminding me, I'll look that up. Or you could look it up. I mean, it's going to be as good as your research, probably. But the order of operations thing, I just don't think it's about right and wrong. It's just about what we agreed we would do and what would come first. So there's an interesting problem on here that I put on here just for that reason. Let me give you this problem. I thought it was on there. Gosh. 6 divided by 3 times 2. So what do you get? What is that?
4.
It's 4. Okay, why?
Because you
So you divide first? Why?
because that's what was agreed upon.
Okay, now that's a problem. If you ask different people, people will answer it differently. If you were to ask me in the way that I was taught, I would definitely say 4. Okay? Because I was taught like this. I think I saw this up in Mr. Zalay's room. It's like this. Right? So the agreement is that parentheses will come first, exponents will come next, multiplication and division, left to right, with no regard, the multiplication is a better division than, neither takes precedence over the other, and it's the same with addition and subtraction, in whatever order they appear from left to right. not all people were taught that way. They were taught multiplication is first always. Okay? So they multiply the 3 times the 2, and what do they get? 6, and they do 6 divided by 6, they get 1. Okay? You get 4, I would get 4, other people will get 1. Okay? So, let me see if I can find it. It's not reasonable at the time. It's got division. It's got multiplication.
Wasn't the whole idea for everyone to do it in the same manner, because math is practically a language? If everyone spoke a different language, nothing would ever get done.
There's, there's an argument to be made there, but the thing, here it is, 13 and 14. The thing is, people get, this kind of question became popular because it was asked on the internet, and then people just went crazy. People were, it's this, like this could be the question. It's 4, no, it's 1. And it was all about who was right. And the truth of it is, this is a poorly constructed, let's call it a sentence. It's not really a sentence, but it's just the punctuation is all wrong. If I want to convey to you clearly what I want you to do, I should really not use a symbol. That's a big thing. That's a big problem. I should tell you, do that. Okay, now I know. Now you know I want you to do those things first. Okay? If I want to be unambiguous, like the guy in the video was talking about, I should put parentheses around it. Okay? Now, a lot of people have agreed to do division and multiplication from left to right. Other people haven't. So it creates a lot of problems. And then people start arguing about what's right. Neither one of them is right. It's just one group agrees to do it one way, and the other agreed to do it a different way. And then these two worlds collide. Okay? And it's just the truth is there's no right way to do an order of operations. There's no way that you agree to do it. Okay? And the way that we'll agree to do it in this class is the way that gets you 4. Okay? 6 divided by 3 because the division is coming first on the left, and then multiply the result by 2. Okay? And the example that he gave, 6 divided by 3 divided by 3, that's a little hard, because this could be 6/3 divided by 3, or this could be 6 divided by 3/3. Right? It could be 6 divided by 3/3, or 6/3 divided by 3. It really could represent either of those things. Where's the big division sign? Which one is it? It's just wasn't planned out very well. If you want to write it that way and you want to convey it clearly, you should really put parentheses around things. Okay? And I bring it up because a lot of you got different answers on, say, a problem like 14. 7 plus y divided by 10x. Now, according to Gordon, what we should do is do the parentheses first. Do we have numbers for y and x? We have 43 and 2. So this is going to be 43, and this is going to be 2. And this is parentheses. We should add these together. Then we should divide by 10, and then multiply the whole thing by whatever x is. Right? According to the order of operations, that's what we should do. All right? Do you think that that's what the person who wrote that had in mind? No? Yeah? They, according to the answer in the answer key, they intended for you to multiply the 10 and the x first, and then divide that by that. Right? You know,
I was going to say, it says there's 10 x's and 2 is x.
Well, it's just saying there's a 10, and then there's a multiplication, and then there's an x. Mm-hmm. Right? Like, I could write just the same thing right here. It says 10x, which draws our eyes, like it makes our eyes draw those things together. But if I wrote 7 plus y divided by 10 times 2, now what would the order of operations tell you to do? Do the parentheses first, add these together. This is supposed to be 43. Should have 43 there. So now according to the order of operations, I should divide this first. From left to right, divide first. 7 plus 43 is 50 divided by 10. That should get 5. Right? times 2 equals 10. See what I'm saying? This PEMDAS thing, this order of operations thing, it's not the right thing to do. There is a convention, there's an agreement that we've made, and part of the agreement is when we write 10 right next to x, we mean to group them on purpose. We mean to group them together, 10 times x. Technically speaking, there's nothing telling me that 10 and x actually are one unit. You should use parentheses there. And so I wouldn't give you a problem like that unless it was to bring up this ambiguity. That's why I put it on the test. And if I did put that on the test, and some of you gave me 10 and others of you gave me, what would that be? 2.5? They'd both be right, because I can't, there's an argument, good argument to be made for either one. They both could be right. See what I'm saying? So, something to think about. So we've just gotten through the first 2 sections here. We got some homework problems. They should go by pretty quickly because they're about adding numbers, distributing, things like that. It shouldn't take too long. Well, thanks. And I don't know if you've ever used Poll Everywhere. Have you ever heard that? You can text, like, I don't know, teachers maybe have used it. You can text a number in a certain way, and it'll like put your text up here in a list or whatever. You can take a poll. Anyway, I have one set up, and it's written on the back board, and it's anonymous. And if you want to, it's in that white piece of paper. If you want to, it's like a suggestion box, I guess, but virtual. So if you want to text me thoughts or suggestions, then feel free to do that. Okay? Any questions? Is this all, yeah? Wish I could cut and paste that. That should be algebra 2, not algebra. Sorry about that. I'll leave it up there and copy it down here. Are we going through it like at a good pace? Am I like everybody's catching on? It is as much review as I'm treating it. Or am I not treating it with enough time? Maybe you could let me know. Yeah. Oh, sorry. Do pass those over here if you would, and have a good day.
Will those be up on your website?
They will, and I'll text them out as well.
Oh, that will be.
So we don't get them copied down.
Yep. You don't have to copy them down if you want to. I'm going to text them out to you. I'm going to put them on the website.